For lesson 7.4, where we're graphing rational functions, I've picked a couple of graphs to help you for this homework assignment that contains a total of 4 graphs. So hopefully looking at these and working through these purposefully will help you as you do the other 2 on your own. So it's basically following these steps. Now the graphs are going to be a little different depending on what the function looks like, but it's this same process working your way through these steps. So let's begin. My first step, I want to find the zeros of this function, and that's another way of saying the x-intercepts. Is this graph going to pass through the x-axis? So let's see. To tell whether or not it does, we're going to take the numerator, make it equal to 0, solve for x. And that's pretty easy. The cube root of 0 is 0. So we're going to have an x-intercept, so I'll go ahead and make that dot there. My graph has to pass through this red point where x is 0. So that takes care of step 1. Now let's see if we have asymptotes. Let's start with a vertical asymptote. A vertical asymptote is a number that we would plug into the denominator in place of x, and when we do, it creates 0. So we're trying to find that number that would create 0 in the denominator if we plugged it in for x, and we've got to basically limit or restrict our graph from going through that vertical line because division by 0 is undefined. So if you're not sure what that number is, you can just take the denominator. This is always true. Sometimes it's obvious what the number is that would make 0. But in this case, you may not know. So you can just take the denominator, make it an equation equals 0, and solve for x. You could have also factored out a GCF and solved it that way, but this is easy enough. You divide by 8 on both sides, and you get x is 4/8, which is another way of saying 1/2. So I'm going to go ahead and draw that vertical line. That is, x is 1/2. So that looks like this. And I always do the asymptote lines in dotted line form because they should stand out from the rest of the graph. The rest of the graph should be a smooth curve all around my vertical and horizontal asymptotes if I have them. Well, let's see if we do have a horizontal asymptote. A horizontal asymptote can be found by comparing the degrees of the numerator and the denominator. And to find the degree, you look at the highest exponent for the variable. So the degree of the numerator is 3. The degree of the denominator is 1. So we saw in your notes that if the numerator degree is larger than the denominator degree, then you do not have a horizontal asymptote. So we don't have to worry about drawing a horizontal line that also serves as a fence or a barrier to our graph. It would keep our graph from flowing continuously going up or down. That's what a horizontal asymptote does. The vertical asymptote is going to prevent my graph from flowing continuously from left to right. So I'm coming this way somehow, and I can't cross over this fence. This is restricted area. This is this is an area that is not able to be on the graph because it creates 0 denominator. Okay, so we've gotten through the first 2 steps, and now we're ready to just make a table. And this is where most of your work is really going to come in. You're going to grab your calculator. And I would also suggest, it's a strong suggestion, if it's possible to do any canceling at this point, you definitely want to do that. In other words, if you could factor and then cancel factors between the numerator and the denominator, that makes putting the inputs a lot easier. But I don't have that opportunity here. I cannot cancel anything. I can't reduce this fraction. So I'm just going to choose some numbers that are around on either side of this vertical line. So basically what I'm trying to do is find out what the graph is doing on the left side of this dotted line that we called x equals 1/2, and what is it doing on the right side of the dotted line. So we're just going to choose numbers, inputs, along the x-axis on either side of the dotted line. Obviously I don't need to choose 0 because I already know I'm passing through 0. So let's test out what do we get for an output if we input -1. And I had some people in class that were struggling a little bit with coming up with the correct outputs. So let me just walk through a few of these with you. So if you input -1 in for both of these x's, it would look like this. You would do -1 cubed. Sorry about that. -1, I guess I can't write on that box. -1 cubed. Alright, and then down here it's 8 times -1 minus 4. Okay, so hopefully you don't need your calculator for this, but a lot of people are a little bit calculator dependent, and I understand that, but it's faster if you could just do some mental math. -1 cubed is -1. And down here we have -8 minus 4, which is -12. And when we put these two fractions together, negative divided by negative is positive. So I get 1/12. That's really, really small. So I'm just going to estimate where I think 1/12 is, right above the x-axis. So I go -1 and then up just a little bit. Okay, well, let's try -2, just to get a feel for where this graph is going as we choose numbers that where x approaches -infinity. Alright, so for -2, basically do the same thing. I'll just erase and replace. So -2 cubed, 8 times -2. -2 cubed is -8. And down here we get -16 minus 4, which is -20. And if you want to just get the decimal form of that, maybe you want to look at all of these in decimal form. If that helps, that's okay. Your table, however, is very important to show. Don't just give me a graph, but make sure you supply a table to support your graph. So 1/12, we can go ahead and put that decimal. 8/20, which would reduce to 2/5, and you probably know what that is. That's 0.4. Alright, so just a little bit more, almost a half. Alright, let's keep going. We can get a good picture of what's happening. -3. If we use -3 as an input, what do we get? Okay, so I've replaced both of the x's with -3, and we'll see what comes out. -27 on the top, -24 minus 4, which is -28. That's almost -1. So we'll do positive 27/28. And if you want the decimal form of that, we can do 27 divided by 28, and that's 0.96. So you can see we're almost at 1 here. So I'm pretty confident that this particular graph, as x approaches -infinity, the y, or f of x, is approaching positive infinity. So if you want assurance, you could do one more. Let's just, again, the number of inputs you use is going to vary from function to function. So -4, -4, -4 cubed is -64. And here we have -32 minus 4, which is -36. And let's just go ahead and do the decimal form of that. 64 divided by 36 is 1.78. A little bit higher than 1. Alright, so you can see how it's traveling. It's following this particular pattern as x approaches negative infinity, f of x approaches positive infinity. Alright, so I'm going to go ahead, and this is a rough sketch based on the table, so I'm going to go ahead and sketch this curve. Okay, so I've passed through 0. Now the only thing I'm not sure about is where is it going to the right of this x-intercept? In other words, does it keep on going? It should. The definition of a vertical asymptote is I should be always approaching but never touching. So it's not realistic to think that it's going to pass through and then just stop. Okay, we always approach forever when it comes to a vertical or horizontal asymptote for that matter. So my big question here is, am I going to pass through the origin and then travel up forever, tracing this dotted line, or am I going to pass through and go down forever? So the best way to know is choose a number for an input that's between 0 and 1/2, and that logical choice would be 1/4. Or maybe you want to do 0.25. Okay, so let's do an input of 0.25 in our function and see what we get. Okay, calculator time. 0.25 raised to the third is 0.0156. And we're going to be dividing by 8 times 0.25 minus 4. That's -2. And now we can divide these together. I mean, if you want to put all this in your calculator at once, that's fine, but I've noticed that some people, because they're not using parentheses properly, they're struggling a little bit with getting the correct output. So maybe you just want to break it up into parts like I've done here, and that might make it just a little bit easier. Alright, so our final output result here would be 0.0156 divided by -2, and that's -0.0078. Well, that's good information because I pass through the origin, and when I travel 1/4 to the right, I'm going down by not much. But what I've established here is once I do pass through the origin, I'm going to travel all the way down this. And if you want more assurance, you could choose another point between 0.25 and 1/2, and that would help you get even more confidence. But here's what's going to happen after we pass through the origin. We're going to go down through this point, and then we're going to follow. We're going to hug the vertical asymptote forever. And sorry about that, but it's tough to draw straight with this thing. But this is an idea of what's happening on the left side of the vertical asymptote. Okay. Now let's see what happens on the right side. So we're going to do inputs on the right side of this dotted line. So let's just start with 1. Okay, so I'm just going to keep on with my table. Alright, and let's put the inputs in. 1 cubed divided by 8 times 1 minus 4. 1 cubed, of course, is 1. This is 8 minus 4, which is 4, so that's 1/4, or you could say 0.25. So as I go right 1, here's x equals 1, I go up 1/4. I'll just say that's 1/4. Very good. Okay, let's keep going. X is 2. So now let's replace x with 2. And we get 8 in the numerator. And we get 16 minus 4, which is 12 in the denominator. And of course that's 2/3. If you want the decimal form, that's 0.67. Alright, so just a little higher. Here's x is 2, and 2/3 is right there. Okay, let's keep going. Let's do one more. Let's do input 3. Well, 3 cubed, 8 times 3. So 3 cubed is 27. This is 24 minus 4, which is 20. And we can do the decimal form of that, which is 1.35. So similar to what happened over here, just going in another direction, if we do input 3, we're going to do an output of 1.35. So I know what's going on going this way. The big question is, what about, again, as I approach this vertical asymptote from this side, is it going to go up from there, or is it going to go down? So let's choose a number in between 1/2 and 1. So the input between 1/2 and 1 that we will use will be 3/4. And if you input 3/4, just save ourselves a little bit of time, we went ahead and calculated that, and you should get 0.21. Okay, so let me back this off for just a minute. Alright, so we've already established that 1 is 0.25, and as we move closer and closer to this vertical asymptote, as we chose 0.75, which is 3/4, we got 0.21. Okay, let's go a little bit closer, and let's do 0.625. That's just another way of saying 5/8. And if we do that, we're going to get 0.24. So if you notice what happens, here's kind of a bigger picture of this. At 5/8 we get 0.24. At 3/4 we get 0.21, which is a little bit lower, and then at 1 we get 0.25, which is a little bit higher. So in essence, we have kind of a dip here, and it's going to start rising based on the fact that 5/8 gave us 0.24. It's going to start a trend that these numbers are just going to continue to get larger as we get closer and closer to that vertical asymptote. So again, it's a little bit trickier, a little bit more, you got to be kind of careful when you get close to the asymptote that you choose the right inputs. And so that's your answer for number 9. Okay, so let's work on number 10 off this same assignment, page 496. We'll start with finding the zeros, so that means to take the numerator and we'll make it equal to 0 and solve this equation. So this is the difference between two perfect squares, so we can factor it. X squared plus 4 times x squared minus 4, and we can solve these factors. Let's let each of these factors equal 0. X squared equals -4. Now at this point, I notice that when I do the square root of both sides, I'm going to be doing the square root of a negative number, and that's not a real number, obviously. That's going to involve the number I. So since I do not get a real number 0, then I can't, that's not going to be one of my x-intercepts. Alright, so remember, zeros have to be, zeros of this function that we're graphing have to be real numbers. So I'm marking this one out, and then I'll focus my attention on this factor. X squared equals 4. So x is going to be plus minus 2. Alright, so I've got two x-intercepts, or two real zeros. Now remember, I've got two other imaginary zeros. I'm not saying they're not zeros, but when it comes to graphing, they can't be considered x-intercepts. Okay, so sometimes I'll give you a problem and I'll say find all of the zeros. Well, in that case, you would include imaginary numbers. But when it comes to graphing and finding x-intercepts, we only use real number zeros. Okay, so there are the points 2, 0 and -2, 0. We're going to have those as x-intercepts. Now let's find any asymptotes. We'll start with the vertical asymptote. Those are values that we plug in for x to make the denominator 0. So a safe thing to do to make sure you catch them all is, like we did with the numerator, just take the denominator and make it equal 0 and solve. And when you solve this, you get two vertical asymptotes, positive 1, x equals positive 1. So here's x equals positive 1. And x equals negative 1. Okay, and now I'm going to do some inputs around these asymptote lines. I need to know what happens to the left of x equals negative 1, so I'll choose some negative numbers. I need to know what happens in between, so I'll choose some numbers in between these two dotted lines, and then I need to know what happens to the right. So let's get to it. Let's make our table. And I think I'm going to wait until I get a feel for the y numbers before I start plotting, because I might need to change the units on the y-axis to make this fit. So let's see. We obviously don't need to input. We can't input negative 1. It's not allowed. And we don't need to input negative 2 because we already know that negative 2 would give us output 0. That's an x-intercept. So let's do negative 3. Okay, so let's have a little discussion before we get into this any further. Sometimes it's better to input into the factored form. Other times it's better to input into the given function. And in this case, let me just show you the factored form of this. If you factored the numerator based on what we have here, this is partly factored and then we just solved from there. But if we factored it all the way, we would have this would be our numerator and this would be our denominator. Now I would not be wrong if I started inputting into this. I would just have to input that number 5 times. Well, in this particular case it makes more sense just to input into the given function because now I'm only inputting twice. However, factoring is important because when you get to this last step, if canceling is possible, it's always better to do that. It helps you graph much easier when you can cancel stuff. Alright, now unfortunately in this particular problem I can't cancel anything, but you should get yourself into the habit of factoring everything you can, and then in some cases you'll want to do your inputs into the factored form. At any rate, you should check and see always, that's why I gave you this little note, you should check to see if canceling or simplifying is possible. Okay, so I can't simplify, and it's going to be easier to use the given function, so I'm just going to erase this factored form. There's no need for you to erase it, I just need more space. But I'm going to show inputs into the given function. So negative 3 to the 4th minus 16 over negative 3 squared minus 1. Okay, so that's 81. Negative 3 to the 4th is 81 minus 16. Alright, so let's see, 81 minus 16 is 65. And then on the bottom I get 9 minus 1, which is 8, and in decimal form that is 8.125. Okay, so right away with negative 3 I'm up here. So let's see what happens with negative 4. You can probably tell that with negative 4 it's going to be a much bigger number. Okay, negative 4 to the 4th is 256 minus 16 is 240. And this is 16 minus 1, which is 15, and 240 minus 15 is 225. So yeah, I'm sorry, I did minus. Back up here, I don't know what I'm doing. 240 divided by 15, 16. Sorry about that. Okay, so I'm definitely going to change my units. I think I'm going to make them in units of 4. So a little tip for you, you may want to wait until you've made some of your table to decide before you just start plotting points, because you may end up changing. You usually aren't going to have to change the x-axis, and I'm okay if you just change the y. So let's plot what we've got here. -3, and then this is 4, 8, and then just a little more. -4, 4, 8, 12, 16. Okay, so it looks like I'm headed in this direction. I know I'm going to pass through this point. Looks like as we choose more negative numbers, we're just going to get bigger. Y is going to approach positive infinity. So I'm okay with what's happening going this way, but I want to make sure that I capture what happens going this way. Does this come through this x-intercept and get to a certain point and then turn and follow? These lines will never just come to a vertical asymptote and stop. The whole idea of a vertical asymptote is we just keep approaching. But I don't really know if it's going to go forever down or if it's going to curve and go back up. So what I'm going to do to find out is I'm going to pick an input in between -2 and -1. So I'm going to use -1.5. -1.5. Okay, let's see what I get. So -1.5 to the 4th minus 16. That's my numerator. Now again, you don't have to show all of this. You can just do all this in your calculator. Just trying to give people something to... Some people are struggling a little bit with just using their calculator correctly to get these outputs. Okay, -1.5 squared minus 1. And that's 1.25. And now we'll do the division. -10.94 divided by 1.25. And that's -8.752. Okay, so I know that if I choose an input here, -1.5, I'm down 4, 8, and about, let's see, this would be 12. So I'm going to go a little bit below the -8. And I'm pretty comfortable with this because it looks like I'm just getting closer. I'm not going to worry about picking another number in between, because it looks like I'm going to continue to get closer and closer. So this is going to be one part of my graph. All right, very good. Now let's check out the middle part. So I'm going to use input 0 to see what's going on in between these dotted lines. So if I input 0, that's a pretty easy output. I get -16 over -1, which is +16. So 1, 2, 3, 4. All right, so the big question is, looks like this is going to be a parabola. If I've got vertical asymptotes that are same distance apart from each other, usually that means I'm going to have symmetry in the middle with some parabola shape. Usually, not always, but a lot of times that happens. So let's take a look at 1/2. So let's input 1/2 and see exactly where that puts us. So I'll just do 0.5, and we'll use our calculator. So raised to the 4th minus 16, and that's negative, I'm going to call that -16, well, -15.9. And then 0.5 squared minus 1 is -0.75. And now I'm going to divide those and see what I get. -15.9 divided by -0.75, and it looks like 21.2. Okay, so for input 1/2, 4, 8, 12, 16, 20, and then a little higher. Okay, and I can be assured now, because of these two asymptotes, I'm going to save us a little bit of time. If I input negative 1/2, let's just go ahead and do it. If I input negative 1/2, well, that doesn't really change anything if you notice, because whether I raise a positive or a negative number to the 4th power, it's going to be the same result. And that's true also for squaring. So for these even exponents, it's not going to matter if I input a negative number, I'm going to get the same result. So let me write that in. So here's the rest of my table. Negative 1/2 is also going to give me 21.2. Alright, so now I feel pretty good that this is going to be a parabola in here. Oh. Well, not a pretty parabola, but it is a parabola. I'm going to be following or approaching, going to positive infinity on both sides. Well, another thing about this function, if you figured out that if I input positive 1/2, I get 21.2, and that's also true for negative 1/2. Well, because of these being even exponents, that's going to be true for these inputs as well. If I just turn around and input the even versions of these, I'm going to get the same outputs by virtue of the fact that these are even exponents. Okay, so I don't think I'm going to use my table. I'm not going to write those into my table. So let's just plot these points. Alright, so I'm going to do 3, positive 3, and that's 8.25 for 8, and then a little higher. You can see I've got symmetry. It's just the mirror image of that point. For positive 4, I'm going to have positive 16. For positive 1.5, I'm going to have negative 4, 8, and then a little lower. And so it's really just the mirror image of that left section. And that's it. We're done. Good job. Okay, so that should take care of 2 of the problems on your homework assignment. And I'm hoping that by doing these, you'll be able to successfully do 8 and 11. If you have any questions, let me know.